Hello, my name is Dave Fout, and I'm a pre-sales engineer with Neo4j, the company behind the Neo4j graph database. Today I'll be talking about how we can use Neo4j to analyze some Bitcoin transactions. Bitcoins are digital coins that can be sent through the internet. It is a decentralized system, meaning that anyone can create a wallet, buy and sell Bitcoins without oversight or regulation. Bitcoin transactions do not explicitly identify the payer or payee, so there is potential for fraudulent transactions. A transaction is a signed message between two Bitcoin addresses. Here's some more terminology to help us understand the Bitcoin network. Addresses are a hash string that is used with a public key to send and receive Bitcoins. Transactions are transfers between addresses that are publicly recorded in the blockchain. A blockchain is the public record of all transactions, and transactions are recorded in blocks, which are part of this blockchain. As we see in this video clip, the Bitcoin network is a connected network that can be analyzed in a graph database such as Neo4j. Once the transactions are verified, they are recorded in a transparent public ledger, i.e. the blockchain. We want to use connected analysis to look at the Bitcoin data. Over time, we would be able to understand and identify normal behavior. In this example chart, we see that there are normal patterns for the number of transactions and the transaction size. We could look at the outliers, those with large number of transactions or large data amounts, but we would likely miss patterns of behavior that we are interested in. Some of the outliers could be valid, as a person may have a small number of large transactions, or they may have a large number of small transactions. I've modeled the data as shown. An address redeems some coins as part of an incoming payment node. The incoming payment node is connected to a transaction which sends coins to an outgoing payment node. This node then sends the coins to an address. The entire transaction is part of a blockchain which is connected to previous blockchains.
Let's talk briefly about downloading the Bitcoin data. For this demonstration, I only wanted to grab a portion of the Bitcoin chain. There are places where you can download the entire Bitcoin database, but I only needed a portion of the data for this demonstration. I started with 4 known Bitcoin addresses. Using the blockchain API, I wrote a Python script that passed in the Bitcoin addresses and received back a JSON document. For each transaction in the JSON file, I parsed out the block height value and called a second blockchain API to retrieve the block index for that transaction. The goal was to obtain a list of all blocks that contain transactions for the 4 initial addresses. Using this list of blocks, I wrote a second Python script that called the blockchain raw block API. This API returns a JSON file with details about the block, as well as details about each transaction within the block. The Python script parsed this JSON file and created several CSV files for the various nodes and relationships that I wanted to create in Neo4j. Using the new Neo4j import option that is available in 2.2, I was able to load the data and create the Neo4j database in less than 2 minutes.
In our dataset, we have 11 million nodes, 14.3 million relationships, and 31.5 million properties. In this demonstration, we will start with 4 Bitcoin addresses, gather the amount of Bitcoins they've received, and then look for common addresses that these 4 addresses have sent coins to. From the common addresses, we will see if there are any other addresses worth looking at. To start off, we will run a cipher query to find an address and its outgoing transactions. We can expand on the incoming payment, transaction, outgoing payment nodes, and finally we have a recipient address node of some Bitcoins. This is a representation of the data in the graph, which aligns with the model that we saw earlier. Now we will query for 4 Bitcoin addresses that we are interested in. These addresses may be involved in fraud by receiving Bitcoin ransom payments. Using Neo4j's cipher language, we will query to see how many Bitcoins they have received. At the current exchange rate of 1 Bitcoin equal to $298 US, these addresses have collected a large amount of money. Next, we will look for addresses that have received payments from 2 or more of these Bitcoin addresses. We run the cipher query that does a pattern match in the graph, and it returns 6 addresses of interest. Let's query these 6 addresses and see how many Bitcoins they received. One address has received over 1,000 bitcoins. This address may be of interest to us. We can again look for common recipients of transactions from these 6 addresses. This query will take a few seconds to return, and when it does, we see that we have 11 results. Using Neo4j, we can easily find patterns within the data and identify addresses of interest. Let's look for recipients of transactions that are about $500 US. This is a common amount in Bitcoin ransom payments. In our data set, we've identified 7 such payments. The address that starts with 1G541 was an address in the previous 6 addresses that had received payments from the first 4 Bitcoin addresses we looked at. Again, this might be an address of interest to us. Let's look at the 1G541 addresses incoming and outgoing transactions. This address has received 33.9398 Bitcoins, and it has also sent out 33.9398 Bitcoins, leaving its wallet empty. Let's look at one final query before we wrap up our demonstration. I want to identify all transaction paths between 2 addresses. We can use the Neo4j cipher allShortestPaths function and quickly return the graph of all transactions between 2 addresses. Neo4j is a powerful tool for performing connected analysis. Using Neo4j, we can easily identify and locate patterns in this highly connected data. Thank you for your time to watch this presentation. Additional information on Neo4j can be found on our website at www.neo4j.com.